many hospitals face a severe shortage of medication supplies and medication in general, which has resulted in the tragic loss of many citizens' lives. Therefore, this study aims to develop a robust AI framework to predict medication needs from ICD code streams and one or multiple medication facilities for the future. So this is my framework architecture for this study, and my framework has three main components. The first component is the ICD encoder, which essentially turns the ICD code time series into one large vector as for the model input. The next main factor is the medication encoder, which turns the medication usage time series into one large vector. And finally, the auto-regressive AI model, which is used to predict the medication usage supply for the future. So, for the ICD encoder, what is it? It works with the ICD code, which is a code that classifies and categorizes diseases, medical conditions, and other health-related issues. However, with 11,000 ICD-9 codes and 68,000 ICD-10 codes, it will be very hard to directly encode the ICD codes. So we have to find a more compact and efficient way to do so. So therefore, we first convert the ICD-9 code to ICD-10 code and group the first three characters of the ICD-10 code, and then use a one-hot vector to represent the ICD code. After this, we perform the PCA, or principal component analysis, which is able to reduce dimensionality of the matrix by creating a matrix called a projection basis, which is essentially is a matrix of a subset of dimensions that help reduce dimensionality. And to make it more stable and general, we use Gaussian noise as well. And here is a complete table of the process. And at the end, we group the ICD code group vectors and stack it together as the model input. Next is the medication usage encoding. So just like the ICD code, we have to represent it in terms of a vector. So how do we do this? Well, we cannot use medication name, as many medications under different names have the same ingredients and also medical usage. So instead, we turn towards ingredients so that our vector represents the ingredients for medication. To do this, we use a list of full medication from the FDA and then use the method TF-IDF to convert the ingredients in terms of vectors, which then can be used for clustering. And then after this, the clustering centers is used as the encoding basis. After this, just like the ICD code encoding, we then use the PCA to reduce dimensionality and while keeping high variance for the medication usage data. So here is a table of the whole process, and just like the ICD code, we then stack the ICD usage vectors into one big vector as the model output. And finally, the last component is forecasting models, where we use a lot of auto-regressive models to show the correlation between ICD code and medication usage vectors. So first is a naive model, which assumes a linear relationship with the medication usages to create a model. And then the vector auto-regressive model, which assumes a linear relationship between the ICD code vectors and the medication usage vectors. And essentially, it's learning to find the matrix coefficients, which is represented by A1, A2 in the equation, to predict medication usage for the future. And finally, we use auto-regressive LSTM, which is from the PyTorch forecasting package, which creates a deep learning model to predict medication usage for the future. And additionally, we use the temporal fusion transformer, or TFT, which is also from the PyTorch forecasting package. And for each model of this, we use quantile loss and stochastic weight averaging to increase the robustness and accuracy of the models. And in the end, because TFT and auto-regressive LSTM are compatible and complement each other, we assemble the models with different lookout horizons to create an additional model. So here are the results. For this study, we used the mimic data where for the ICD code we used the diagnosis table, and for the medication usage we used a prescription table and a event table. And after doing the process, we then mapped the model output to medication usage as shown in the table below. So the table below shows the predicted medication usage value versus the ground truth. And as you can see, the ensemble model is more accurate compared to the other ones, which is why in this study we will be using this model as our final model. So using the ensemble model, we're able to predict the medication usage for the future as shown in the graph above. And additionally, we can also predict the ICD code stream frequency for the future as well, which will help with logistic planning for doctors and other medical workers. So overall, the performance for the ensemble models achieved an average error of 5.2% for 5th day forecast and 18.1% for 10th day forecast. However, although the performance is relatively okay, it's not consistent for all medication, as other medications have an error of over 50%, which means that our framework still needs some work to do. So, given the nature of time series models, it is a dynamic and non-static. It is dynamic and non-static, which means that as time goes on, AI models will perform worse and worse. So to combat this, we use the Bayesian change point detection algorithm, which detects if there's a big forecasting error. And if there is, we then fine-tune the model to weigh more on the latest data points. So in the future, to improve this study, we can create more robust vector representation for ICD code and medication features. We can also improve assemble methods, performance, robustness, and reliability. Adapt the framework to dynamic conditions like pandemics and outbreaks. Use intelligent tools for managing healthcare logistics, especially under extreme conditions. And further detailed examination of the system performance improvement. We can also address the system limitations and interpretation capabilities, evaluate the framework of COVID historical data, and apply the framework for different use cases, non-medication medical supply forecasting. Thank you. And any